So, first time ever.
That calls for celebration.
It was 8.5. So recall from 8.5 that the solution for the system x prime equal to ax can be written as x equals fundamental matrix phi of t times some constant column vector.
Is this the thing with like you get the initial value and it has to become
That was the special matrix. So no.
Oh.
Maybe that's what you were thinking of.
I was thinking of the special matrix. No, this one was okay.
Okay, yeah, this isn't too bad.
Yes, now I'm excited again.
Yes, wine for the world, class. Wine, wine, wine.
create a win from the
I'll
class.
do it for all.
Okay, so the idea that we're going to proceed with here is one and the same as what we did the first time we talked about variation of parameters. We're going to take our constant and we're going to say, you know what, let's pretend that's some sort of column matrix that could have functions instead of just constants. And maybe that'll help us. So that means instead of C1, C2, C3, we'll now have functions U1 of t, U2 of t, and so on. U sub n of t. Okay? So then what we're going to do is let our particular solution take this form. So fundamental matrix times U of t. So now we're going to take a look, and if this is what our particular solution is going to look like, we're going to plug it in and see what needs to happen so that we can work with this formula. Okay, so if we plug it into the system, x prime equal to ax plus, now we have some function. Okay, so it's a non-homogeneous system. So we have something added to it, like we did last section. If we plug it in, now on the left, well, let's just figure it out one at a time. The derivative, of the particular solution, if we use the product rule, would be phi of t times u prime of t. And this is quickly dying on me. Let's try this color. Plus phi of t prime times u of t. Okay, so this is the left side of our system.
What's that notation under the...
That was me messing up.
Oh.
Ignore that. Okay, so then on the left side, we have what we just calculated. Bless you. And now on the right side, we have a times x, so that'll be a. And then x is going to be our particular solution, which is phi of t, u of t, plus f of t. Okay, so this is what we have.
Wait, so U of t is the same as C?
That was the, yeah.
What's the, is there like a purpose in using the different letter?
Well, C represents constants, U represents of functions instead of just constant parameters. Hence the name variation of parameters. We're changing it from constants to actual functions here. Okay, so now this is going to look nice in a little bit. The claim is that, and we'll prove this, it's, oh, settle down.
instant orange.
We need to know.
You don't need to know this part, no, but I'm going to explain it so that it's not just like, oh, okay. If the derivative of the fundamental matrix is just A times the fundamental matrix. Okay, and this is why. Since X equals fundamental matrix times C, and the system X prime equals AX, if I go ahead and calculate X prime would be what? Well, not that side. Phi prime C, okay, and then that has to equal
Oh, so this is a constant? AX?
AX,
So AF, or A phi C.
A, Phi, there you go, C, good. Well, pretty much there it is. Phi prime of t must equal A times phi of t. Okay? So now using this fact, in here, let me switch colors again. Maybe this orange works. If I plug that in, that's not working either. Let's try green.
Last day of the
Yeah, it's like these markers almost made it the whole year. Okay. So if I go up here and replace phi prime of t with A times phi of t times u of t, and again that equals A phi of t u of t plus f of t.
Yeah, like at this point, I don't know what any of them are. So I'm trying to get it on the page.
This is the fundamental matrix of solutions, so it consists of x1 as a column, x2 as a column. Well, yeah, that's the whole point. So these cancel. Okay. So now we have phi of t times u prime equals f of t.
If I define what there's going to be a question mark, if the class inclines at a rate of this much per unit,
And the tears
Don't
are
give them
flowing
ideas.
from
Wait,
the
what?
face at a rate of this many
and
years.
this will be
This will be like
instead of
That
the tank
dissolves.
question, it's going to be students are relieved when I say I'm cutting their I'll push the test back at a rate of 1 tear per day.
What?
I feel like that's hard, and I don't want
We're
to.
talking
Guys,
about-
I don't think my hundreds of YouTube followers want to hear you complain about math. All right.
You should just do a problem
You get a
about
life.
the rate at
That's
which
why
kids
I'm
come
making
into
this
the
so
classroom.
Yes, that is why. They tune in solely to hear you complain.
Yeah, I would
Okay.
There you go.
All right, so here's the thing.
Making YouTube.
Ultimately,
Complaining about-
what we really want to figure out is u of t, because that's going to help us go back and that'll be our particular solution. If I know fundamental matrix, which we will, because that'll be constructed from our solution set for the complementary solution. If I can find u of t, then I'm done. And here's the link. Here I have the derivative of u of t. Okay. Now, how do I get rid of a matrix? You have to do the inverse, yes.
Yay.
So you do the inverse of the fundamental matrix to both sides, and it's got to be in this order. So now we get that u prime of t equals the inverse of the fundamental matrix times f of t. And if you're wondering why we would ever integrate a matrix, here you go.
What?
Didn't you ask like at the very beginning when we started matrices, will I ever have to integrate
I probably did.
Jinxed it.
Okay? So, instead of what we did yesterday, which was, well, we have sines and cosines, so maybe our particular solution is a cosine matrix and a sine matrix with some constants or whatever. Or if we have a linear function, then we have t and we have a constant matrix. This is a much more refined way of finding the particular solution because it's not limited to just sines and cosines and polynomials and exponentials. Like this will work as long as we can integrate the inverse times f of t, we can always use this method. Okay, so then our particular solution, which, where is it? It's phi times u, right? So that means we're going to take fundamental matrix times the integral of the inverse of the fundamental matrix times f of t dt. Okay, so this will be how we find that particular solution. Okay, and all I have is one example to go through. Did you have a question, Drew?
No, you're answering.
Oh.
I really think that the only numbers on this page are 8.5.
And 8.5.
This is literally all
The one
symbols.
for the inverse.
Oh my gosh. This isn't even math anymore.
Oh, this is math.
So
This is like your
This-
extended
This is the
numbers.
math that.
I
people
want
don't-
addition.
For those of you that will go on to study more mathematics, you're not going to see very many numbers anymore.
What?
Math is not just the study
Why
of.
am I going into engineering?
Yes.
Well,
Jacob.
engineering brings in numbers.
What,
Yeah, physics brings in numbers mostly. Those statistics is also
when do we use answer?
simple manipulation.
When?
Yeah.
To find the particular solution of a non-homogeneous system.
I did it.
Like what, like the ones we did in A7.
You could use that for those too. This is an all-encompassing, like, you can always use this method.
A last resort. So if the one, if yesterday's method doesn't work.
Okay, freshmen. Oh, sorry, you guys aren't freshmen. Settle down.
If undetermined coefficient doesn't work, then we use this.
Yeah, so I mean, it really depends. It's a matter of preference. If you like yesterday's method and you see that you can just do it that way, you can do it that way. If you see a system that's kind of unusual and has maybe, I don't know, like a secant in there or something that we haven't really talked, then I would stick with this. Okay,
So,
but
like-
this will work regardless of, like I said, as long as you can find the inverse, multiply with f of t, and find that integral, your options are limitless. Okay.
And all of those symbols represent a matrix.
Yes. Yes, these are all matrices.
I feel like I learned more of a foreign language in this class
And
than
to
any
make
other.
it the integral of a matrix, you like change the integral.
You
to,
just
like,
Besides
Each
it.
Yeah. So here's the example. Okay. You know, last lesson I get to teach you guys, and all I hear is
I think
whine,
we've
whine,
stayed on
whine.
track.
We
I
need
think
to,
that's what
we need to make up
matters.
for yesterday. I don't think there was much whining yesterday.
Yesterday was fine.
We need to stay on brand for the last.
Is yesterday?
We need to make a name for ourselves. Whining is fun.
Okay. So here's the example. Now, I should mention, yes, we could do this with undetermined coefficients, Jacob, since you asked, right? You can do, particular solution would be a1, b1 times e to the t, and then b2, a2, b2 times t. Okay, you could try it that way. But let's go ahead and solve the system with this new method. So first we're going to find the eigenvalues and vectors so we can find our complementary solution. So the determinant of a minus lambda I will be -6 minus lambda 2, -3, 1 minus lambda, the determinant of that. So that will be -6 plus 5 lambda plus lambda squared plus 6. So that works out nicely. So we have two eigenvalues, 0 and -5, yes. Alright. Let's go for the first one. I mean, you can kind of suspect 0 would have been an eigenvalue, right? To start, seeing that these are multiples of each other already. Eliminating the bottom row and dividing by, or multiplying by negative a sixth gets you the usual 1, negative a third, 0. So k1 will equal 1/3 times k2. So one choice for an eigenvector would be 1 and 3, yeah. Yeah, if you do 3 up here, this would have to be a 9, right, for k2. Okay. For lambda 1 equals negative 5. Oh, yeah, sorry. Now we want to do a plus 5i augmented with 0. So add 5 along the diagonals. You got negative 1, 2, and then negative 3, 6. You can clearly see their multiples again. At this point, you know that we're going to get zeros in the bottom row. This is 1, negative 2, 0. So k1 equals double k2. So our second eigenvector, 2, 1 would be fine. Okay, so our complementary solution would be what? Oh no, I always do that. Instead of writing a fraction. C1, 1, 3.
Because you think 1, that's over the 3, 1 over 3.
Yeah.
That's
I
C2.
do that when I do like permutations. And see
Oh, I do that
if
too.
C is 1 divided by 3.
Good. So there's our complementary solution. And let's go ahead and find the particular. So for the variation of parameters method, we're going to let the particular solution take the form of the fundamental matrix from this solution set times u of t. And we're going to have to find u of t.
What is the fundamental matrix?
That's a great question.
We did it somewhere.
We did do it somewhere. It's actually very easy.
It's like everything put together.
It's solving the fun.
Somebody said it.
No, I wouldn't have said
It's the fundamental matrix is just the solutions from your complementary solution. So like, you know how this is x1? The fundamental matrix has x1 as a column. This is x2, right? x2 would be the second column of the fundamental matrix. So if we had a 3 by 3, you'd just have a 3 by 3 fundamental matrix. Okay? So now here's the fun part, because we get to review finding inverses. Okay? Yeah, so
Oh, you have to do this thing where you cover one. Like,
yeah,
and
that
then
was
take
the C sub ij stuff, right?
Yeah.
Luckily, I'm behind on the homework, so I do that.
I remember how to do that.
Yeah,
You do or you don't?
I do.
Okay, so what would this entry be here?
That would be e to the negative 5t. The one next to it would be negative 3. Because you switch the sign.
Oh, it's better with the 2 by 2.
And it's a
Right?
3 by
Don't you swap it the other way?
It's
I thought you don't have
It's e
to
to the
swap any
negative
with
5t.
the 2 by 2.
the negative 3,
No.
the negative 2 e to the negative 5t.
No, you only swap it over the diagonal, so it'd be -1. Or would it be positive negative
Wait,
1?
you have a 1,
Think
1,
of the
no,
positions.
That
This is 1,
one.
1.
That's 1, 1. That's
That stays, right? What would this next number be?
-3.
negative 3 because
Yes.
it's the
Negative-
thing
And then
with
it'd be
the
-2 e to
odd
the
power.
5t. And then we're just.
Yeah.
And this would be
And that's
1.
1.
So now, and by the way, we should also find the determinant.
Wait, is it still negative 5t?
I thought
Yes.
I thought you flipped it like over the diagonal. So it was a 1 in the.
We haven't finished. Settle down. Settle
You
down.
have to still take the transpose of that.
Oh, that's not okay. Yeah, that's not the transpose yet.
No, it's not. Okay, so the determinant of this would be what? numbers.
Negative 4 e to the
Negative 5 e to the negative 5t, right?
Because 3 times 2 is 6, not 5.
So then the inverse
Great, maintain your circle.
is going to be 1 over this. And now we take the transpose of this matrix. So that'll be e to the negative 5t, negative 3. For the first column, negative 2 e to the negative 5t, and then 1 for the second column. So far, so good? Okay. Not happy?
No,
Why?
because I have to do this stuff.
Should have done it already. Okay. So now let's go ahead and find the inverse multiplied with f of t. So what would the inverse be? Let's see. If I distribute, the e to the negative 5t cancels from that first spot. So all we have is negative what? And then here we have good. And then f of t, negative 1/5.
Where'd the
E to the
negative
TT.
5t go? Where'd the
E to the
negative
TT.
Same thing from the.
No, but we're Andrew, what are you talking about?
Oh, never mind. Wait.
Are you ahead of me?
No, I don't think so.
Wait, shouldn't that be negative
think
1
Andrew's
over
ahead of all of
5
us.
e to the negative
What was
5?
in the F of T matrix?
F of t was, that's what I was about to do.
Is that the,
E to the tt.
is just that?
So that's this one.
Okay, yeah, never mind.
What? Wait,
It's from the
I'm
From
sorry.
the,
given product. I thought you already multiplied.
No, that's what I figured.
Right?
So now if we go ahead and multiply this through,
Andrew's already always one step
Wait, I
ahead.
Yeah.
get it now. I get it now.
now we're going to get negative 1/5 e to the t plus 2/5 t, and then 3/5 e to the 5t, 6t, minus 1/5 t e to the 5t.
and it's a column.
That's the 60, yes. And this is now a 2 by 1, right? So now we want to find the integral.
That's easy.
Yeah, it is.
Yeah, that's not.
Except we won't always get it.
It's probably the nicest one we get, actually. No, it'll always be.
Will
Wait,
you
and then we
always
have
try
to
to
still
give us something
multiply
that
this
will
by
be
5?
If it's an indefinite integral, you have to evaluate
Yes.
the constant
Okay.
matrix at the end.
I'm doing it piece by piece.
Well, I don't think it'd be constant matrix in this case. It would be a constant.
Yes.
6?
Yes, it's 6, yes. I just keep making it even worse and worse.
Yeah.
This is a 6. By the time the fourth person adds, it's just going to look like a blob.
Is that a baby?
Okay. So now we're going to go ahead and integrate this matrix.
You're adding constants.
And when we integrate, let's see, the first part isn't so bad. That's just going to be negative 1/5 e to the t.
Wait, how do we integrate the last thing? No.
We didn't integrate yet.
Minus
Oh.
what would this be? 1/5 t squared?
We did
No, you could just do
You could do tabular.
It just subtracts
Yes,
the
this is a plus, thank you. And this part will be 1/10 e to the 6t. And then, yeah, so you're going to have to do integration by parts here. Or tabular, whatever you want to do. Tabular is pretty quick here. Negative 1/5 t, negative 1/5, 0. And then we integrate e to the 5t. So that's e to the 5t, 1 over 5 e to the 5t, 1 over 25 e to the 5t. And then we go that way. So, what's this going to be? One over 125 e to the 5t. Okay? Almost done. Well, no, the constants will take care because we have the parameters already plugged in the solution. So all we care about is just this integral part. So our final step to find the particular solution is to take this result, multiply it with the fundamental matrix.
Should there be like a T in the middle term there, on the last row? Right?
Yes, that should
Negative
Yeah.
whatever.
Right here?
be.
Oh yeah, I missed that. That should be, oh, here it is. Okay. Now we're good. So now we're going to multiply that with the fundamental matrix. So that was what again? 1, 3, 2 e to the negative 5t, e to the negative 5t, multiplied with this. No. Forever? Your concept of forever and forever are two very different things.
Everything math related takes forever.
All right, so if we go ahead and multiply this out, take 1, multiply it to the top row. Take the second entry, multiply it to the bottom row. Now that becomes plus 1/5 e to the t. And then, oh, I should have had more space. That's okay. Minus 2 25ths t. Oh, that's nice because the e to the 5t and the e to the negative 5t cancel. Plus 2 over 125. And if we do the same thing with the bottom row, negative 3/5 e to the t plus 1/5 t squared e to the negative 5t. Oh wait, I'm getting ahead of myself, aren't I? 3 times that, yes I am. Just 3/5, that's my bad. 3/5 t squared. Yes?
Yeah.
And now we go to the last entry and distribute that to bottom row. So that'll be plus 1/10 e to the t minus 1/25 t plus 1 over 125. So now we can clean this up a little bit. Some things should cancel. The negative 1/5 e to the t cancels there. So now we're left with 1/5 t squared minus 2 over 25t plus 2 over 125. And then anything cancel out here?
The e's and the t's can combine.
That's true. So that's 5 minus 3, 2/5, or 2/10, so 1/5. And 3/5 t squared minus 1/25 t plus 1 over 125.
Isn't it 1/10 minus 3/5?
Did I screw that up?
Times
Negative 6 plus 1 is negative 5/10. Yes. Thank you.
Wait, what? Is that 2.5?
Is what? That's a 2, yes.
Oh yeah, it is negative.
Okay, so there's our particular solution.
Is that it?
Pretty much. So now we just write it. X equals C1, 1, 3 plus C2, 2, 1 e to the negative 5t plus this mess. Okay? Complementary plus particular, as usual.
Would this have been easier to do the other way?
Why don't you work it out?
And you don't have to put C3 because it's particular, right?
That's correct. Yes.
So what if our
Sorry?
imaginary